Hello, today we will be doing homework for part D. First, we are going to explain how cascade control can be used to enhance the control of an exothermic reactor by adjusting the flow of the cooling water that is in the cooling jacket. Then we are going to draw out the block diagram and derive the transfer functions. And then we're going to simulate a few examples in Colab. So we can start out by drawing our system here. We have a reactor that will have an agitator inside of it, and this reactor will have a jacket around it with cooling water going through it. And the jacket will have a probe. I'll use green. It will have a probe right here measuring the temperature of the cooling water. So it will measure the temperature of the cooling water. And then there will also be a probe inside of the reactor that will be measuring the temperature of the reactor. And these temperatures will also have set points. So the reactor, there will also be a T reactor set point, and there will also be a T cooling water set point. And there will be a flow going into this reactor and a flow coming out. And there will be 3 parameters of the flow going into the reactor that we'll be able to control. One of them being Q, the flow rate, another being temperature, and then another being concentration. So these are 3 things that can be controlled going into the reactor. And so this probe right here, the cooling water temperature probe, it will actually be connected to a controller that will flow into an automated valve here that will control, or that will be the inlet of the cooling water. So it'll be recirculated. So this is where our cascade control comes in. And we use cascade control because the cooling water coming in is controlled by what that reading is over here, the reading of the temperature of the cooling water. It's being it is controlling then the flow that is coming in, so that we reach the set point that we want of our cooling water. So that is part 1 of our homework here, and now we'll move on to part 2. And part 2 is to just draw the block diagram from D1 and to derive the transfer functions that relate the reactor temperature changes to changes in the set point. And then we'll look at disturbance as well. So we can start out here. We will have first G reactor, the transfer function of our reactor temp control. And this will go into a controller here, which will then flow into the transfer function of the jacket temperature control, which will then flow directly into the transfer function of just the jacket, G jacket, which will then flow into another controller that will be connected to the one over here, which is showing this connection over here of this probe over here being directly connected to the flow of what is being recirculated through the cooling jacket. And so after that, we will have our transfer function of just our reactor. So we have our reactor control or reactor temperature control, which then goes into our jacket control, which is kind of in the middle there. And then we get to our transfer function of just our reactor over here. And so now we're going to have a series of 3 other controllers over here. And the reason we have 3, it's related to these 3 parameters that, that I talked about earlier. The 3 parameters that can be controlled with the flow that is going into the reactor. So first, let's just say this first one is temperature. So this will have a transfer function we'll just call GT for temperature, and our temperature that we set is going into there. And then we will do concentration next, so GC, and our inlet concentration is going into there. And then here we will have GQ, which is the flow rate of the inlet. And so this is outputting the temperature of our reactor. Okay, sorry, it's kind of long here. And then over here at the beginning, we have this device going into here. We'll have a control there that is connected to this output here. And then into here, we will have our T set point. All right. So there's a lot going on here, so we can simplify it really quick before we derive our transfer functions. So to simplify this out, I'm just going to call our input and output, instead of T, I'm just going to call it Y because that's what we've been calling in CoLab. So our Y set point is going to go into that controller there, which will then go into a transfer function here, and this will be GC2, which will go into another controller here that will go into GC1, which will flow directly into GP1, which will flow into another controller that will flow into GP2, which will flow out into our Y. And so this will be connected once again, and then this will also be connected on the outside here. And we will have a disturbance coming in for this one. I'm going to move it down a little bit. So we're going to have a disturbance flowing into this controller here. It's going to be GD, and a disturbance D is going to be flowing into there. So now we can begin deriving our transfer function here. We can start out by saying Y is equal to GP2 times Z. And we can say that Z is equal to GD times D, our disturbance there, plus GP1 times GC1 times E minus Z. And so Z times 1 plus GP1 GC1 equals D times times GD plus GP1 GC1 times E. Okay. So therefore, dividing everything by this here to get Z alone, get Z equals D times DG plus GP1 GC1 E over 1 plus GP1 times GC1. So now we need to define our E portion here. So E is equal to GC2 times our Y minus our Y set point. So if we plug this into up here, we get Z equals DGD plus GP1 GC1 and then times GC2 and then times Y minus YSP all over 1 plus GP1 GC1. So now we want to get Y alone, so I will come up over here, get Y equals D, G, D, GP2 over 1 plus GP1, GC1, and then plus or it'll be times Y minus YSP, GP1, GC1, GC2, GP2 over 1 plus GP1, GC1. So then we get Y times 1 plus GP1, GC1, GC2 over 1 plus GP1, GC1 equals D, G, D, GP2 over 1 plus GP1, GC1 times D, and then plus GP1, GC1, GP2, GC2 over 1 plus GP1, GC1, and then that will be multiplied by our set point of Y. So to simplify this out a little bit, because this is a lot, we can say that this right here is beta, this is alpha, and this, it's beta as well. So now we can simplify this again. So we can say Y equals, this is also beta over here. So we can say Y equals alpha over 1 plus beta, because we have that 1 here. That will be times D, our disturbance, and then plus beta over 1 plus beta times our set point. So here is our transfer function for our system. And now we can move on to part 3 of this homework and code out a few examples in Colab. All right, so I did forget to write a GP2 right there. So now those betas are equal. But now we will get into the Colab portion. I went ahead and put in some values and equations from our problem statement over here, just so we don't have to keep going back and forth. And so to get started, we can define our alpha and beta. So our alpha is equal to, I'm just looking at it on my iPad, our GD1 times GP2 divided by 1 plus GP1 times GC1. And then our beta is equal to GP1 times GP2 times GC1 times GC2 divided by 1 plus GP1 times GC1. Okay. All right. And now we can get into generating plots. First, we are going to start by plotting our inner loop disturbance. Oh no. Okay. Okay, my internet went out, but I think it's okay now. Hopefully video didn't get lost. But so we're doing our inner loop disturbance first. We're gonna plot that out. So we can do t comma y underscore disturb equals sim, and then we want to simulate alpha divided by 1 plus beta. We want lambda t to be 1, n equals 500, and dt equals 1. And then we will make our subplots here. Big.add scatter x equals t, y equals y underscore disturb, mode equal to lines, okay. Oh no, my phone. Okay, 1 second. Okay, sorry for the technical problems. But yeah, here's our inner loop disturbance graph here. We can see it oscillates and reaches a steady state around 0. Now really quick, let's plot our outer loop so that we can compare the two. Going to do ty underscore ty underscore reactor, and this is going to be sim, and then we want to do our reactor transfer function, which was beta over 1 plus beta. So beta divided by 1 plus beta. And then we want Lambda is going to be the same, 1, n equals 500, and then dt equals 1. And then we will make our plots again. X equals t, y equals y underscore reactor, mode equals lines. Okay, so we can see that there's a little more like oscillations in the early behavior of our inner loop disturbance, and that this inner loop disturbance kind of goes up and down, whereas the outer loop, it doesn't really ever go below its starting point. It doesn't, like, whereas this one goes below 0 into the negatives. But this one, our inner loop, goes steady around 0. Our outer loop eventually goes steady around 1. So this is our servo control down here. And this is, we can see our disturbance here. So I think that is all that the problem asked here. Yeah, so we looked at the servo control and we looked at the disturbance rejection as well. So I think that is all for homework 4 and process controls and dynamics. So thank you for watching and have a good summer.